Okay, so let's learn about proof by contradiction, and then I'll do contraposition on the next page. So proof by contradiction, here's the deal. So we're going to suppose the statement to be proved is false. That is, we're going to take the negation of the statement. So we take the negation of the statement, we show that it leads to a contradiction, so that means that the original statement is true. Got it? Take the statement, take the negation of it, show that that's wrong, and so if it's not false, it must be true. All right, so let's look at this example here. So this one's all written out for you. So prove that there is no integer that is both even and odd. Okay, so that means for all n's in the integers, right, there's no n that's even and odd at the same time. So let's suppose not. So the first step is always taking the negation of the statement. Good thing we have practice on that, right? Okay, suppose there is, right? So the negation of a for all is suppose there exists, right? An integer, and the integer, that is both even and odd. Okay, so if n is even, then it's equal to 2k. If n is odd, be careful, 2t plus 1, not 2k, 2t plus 1. Because you have to have different integers, right? We don't want to say that they're just the same one apart from each other. So k and t are integers. So we always have to start here. So be careful that you start with, okay, here I am, you're communicating to your reader. N is the same thing as n, and I'm going to put in for n 2k on the left side and 2t plus 1 on the right-hand side. So then I'm going to pull the 2t over to the left side, factor out the 2, and I'm left with k minus t is equal to 1/2. So what do I know about k and t? K and t are integers. So if I take two integers and subtract them, their difference must be an integer, but it's not. That's the contradiction. And so you just have to say this in words, and some people like to use this kind of circle with an X through it. That means that that's a contradiction. So since this is false, this must be true, right? This is false because we just proved it. So then that must be true. So we've proved by contradiction. I'm going to let you do this one in class, or you can practice with that, and we'll have someone present it. Let's do this one that's a little bit different. Suppose there is no greatest integer. Okay, so prove by contradiction. So that suppose there is a greatest integer. Okay, so I'm going to say that I'll just use capital N to be the very, very biggest, right? It's the big guy, where capital N is bigger than all, right? For all the other n's, capital N is bigger than n, all the n's, all the integers. Okay, so from this true statement here, I'm going to add one, because I'm allowed to do that with integers. Whoa, wait a minute. I just found n plus 1. That's bigger than n. So that's a contradiction because I said n was the biggest, and now I just made n plus 1. So that's a contradiction. So this is false. So that must mean this is true, right? If I show the contradiction is false, that means the original is true. All right, so let's continue on with this next one. Okay, so prove by contradiction that for all real numbers x and y, if x is irrational and y is rational, then x minus y is irrational. Okay, so suppose not. So this is a necessary step to kind of communicate to your reader, me, and whoever you're reading your proof, what you're doing. So suppose not for an all is there exists an x and y in the reals reals, let's make that a little better, right? Such that remember okay, here we go. How do you take a negation of an if-then? There is no if-then in your negation, correct? Okay, so to take the negation, you would say this is still true, and there's no notation for irrational. So you just have to write out irrational. So this stays true, and we negate this. Oh, I'm sorry. Nope, I forgot. This is all of this is the if, right? Okay, so I have to say and y is in rational. Remember, y rational is q. Okay, so this and not this. So x minus y, I could say not irrational, or I could say, oh, it's rational, right? So the negation of the if then is this and not this. Okay, so now let's move forward with what I know. I don't have definitions for irrationals, but I have definitions for rationals. So let's start with that. So I know that y, being in the rationals, must be an a over a b, a and b in the integers, comma, b cannot be 0, right? Okay, so then I'm looking at what x minus y is, right? So x minus y, so and means this is happening at the same time, right? X minus y is supposed to be, and I'll have to use different letters, a c over a d, where c and d are elements of the integers and d doesn't equal 0. Okay, so now let's combine these things together. So let me just write this up here again so you can see what I'm substituting in. Oh gosh, that's supposed to be messy C. Okay, there we go. All right, so now let's substitute in for y. No arrows, right? Minus a over b equals c over d. So let's add this over, right? Add this over, so I'll get c over d plus a over b. So then I'm going to make common denominators. So let me just come up here. So I get CB plus AD all over DB. Okay, so what do I have here? I have X. So what I've done is I've rewritten X as a quotient of integers. So if I let P equals CB plus AD, because it's a product and addition of integers, so that's an integer. And I know, and if I let let me make sure you use a different little q equal db, and the q will be an element of the integers, and I know that q does not equal 0, and I can just say by the 0 property, right? Because I know that d doesn't equal 0, and I know that b doesn't equal 0 because I stated it here. So what have I done? I've shown that x can be written as p over q. What does that mean? That means x is rational. Is x supposed to be rational? No, that's the contradiction, right? The contradiction. X is not rational. So there it is.